Now let me tell you about a slightly faster way of doing it. Actually, it's not much faster. It's pretty much the same calculation, but it's maybe more enlightening. Oh, let me actually show you the nice color picture that I prepared for this. Okay, so, right. So one thing that's on this picture that I haven't drawn there is the normal vector to the plane. So why is that? Well, let's say that we know how to find a vector that's perpendicular to our plane. Then what does it mean for the point P to be in the plane? Well, it means that the direction, say, from P1 to P has to be perpendicular to this vector n. Okay? So here's another solution. So P is in the plane only when, well, exactly when the vector P1P is perpendicular to n, where n is some vector that's perpendicular to the plane. So that's called a normal vector. Not that the others are abnormal, but okay. So how do we rephrase this condition? Well, we've learned how to detect whether two vectors are perpendicular to each other using dot product. Okay? Dot product. That's the first lecture. So these two vectors are perpendicular exactly when their dot product is 0. Okay? And so now, concretely, well, if we have a point P1 given to us and say we have been able to compute the vector n, then, well, when we actually compute what happens, here we will have the coordinates x, y, z of a point P, and we'll get some condition on x, y, z. That will be the equation of a plane again. Okay. Now, why are these things the same? Well, before I can tell you that, I should tell you how can we find a normal vector. But maybe you are already starting to see what the method should be, because we know how to find vectors perpendicular to two given vectors. Right? So we know two vectors in that plane, for example, P1, P2, and P1, P3. Actually, I could have used, another permutation of the points, but let's use these. So if I want to find a vector that's perpendicular to both P1, P2, and P1, P3 at the same time, all I have to do is take the cross product. So how do we find this vector that's perpendicular to the plane? Well, the answer is we can just take the cross product P1, P2 cross P1, P3. I should say, well, say that actually you took the points in a different order. You did P1, P3 cross P1, P2. You would get, of course, the opposite vector. That is fine. Any plane has actually infinitely many normal vectors. You can just, multiply the normal vector by any constant. You will still get a normal vector. That's absolutely fine. So that's going to be one of the main uses of dot product, C. When we know two vectors in a plane, it lets us find the normal vector to the plane, and that is what we need to find the equation. Now, why is that the same as the answer over there? Well, the condition that we have is that P1P dot n should be 0. And we said n is actually P1, P2 cross P1, P3. So this is what we want to be 0. Now, if you remember stuff from a long time ago, that was Friday, then we've introduced this thing and called it the triple product. Okay, and what we've seen is that the triple product is the same thing as the determinant. So in fact, these two ways of thinking, one saying that the box formed by these three vectors should be flat and have volume 0, and the other one saying that we can find a normal vector and then express the condition that a vector is in the plane if it's perpendicular to the normal vector, they're actually giving us the same formula in the end. Okay. Any quick questions before we move on? Yes? So these two quantities, P1, P dot cross product, or the determinant of the free vectors, they're always equal to each other. Okay, they're always the same. And now if a point is not in the plane, then the numerical value will be non-zero. If P is in the plane, it will be 0. Okay, let's move on and talk a bit about matrices. So probably some of you have seen about matrices a little bit in high school, but certainly not all of you. And so anyway, let me just introduce you to a little bit about matrices, just enough for what we'll need later in this class. I should say, if you want to know everything about the secret life of matrices, then you should take 1806 someday. So, okay, so what's going to be our motivation for matrices? Well, in life, a lot of things are related by linear formulas. And even if they are not, maybe sometimes you can approximate them by linear formulas. So often we have linear relations between variables. And for example, well, if we do a change of coordinate systems, so for example, say that we're in space, well, and we have a point, so its coordinates might be, let me call them x1, x2, x3 in my initial coordinate system. But then maybe I need to actually switch to different coordinates to better solve my problem, because it's more adapted to other things I will do in my problem. And so I have other coordinate axes. And then in these new coordinates, well, it will have actually different coordinates. Let me call them, say, u1, u2, u3. And then the relation between the old and the new coordinates is going to be by linear formulas. I mean, especially if I choose the same origin. Otherwise, there might be constant terms, which I will not insist on. So let me just give an example. For example, maybe